in this box. So he has so many continuous variables. Suppose here is a SBP1, that is systolic blood pressure. I assume that follow the normal distribution. Okay, I assume that this follow the normal distribution. So I got, this is my observed variable, and here is 745 individuals here. So from here we got mean and standard deviation also. Now I want to compare.
Sorry, sir, for disturbing. We are now in live in YouTube. Sir, let me share the screen first. Then you will again start your session. Please stop your session, sir.
Oh, we are not. You are not visible. This one.
No, I am visible. It is visible, sir. Please stop your screen first. Then I will explain about this course because we are now in live in YouTube.
Okay.
Just a minute, sir.
I stop this. Stop sharing.
Yeah, please stop sharing, sir.
Oh.
Good evening, all the participants and our resource person, Dr. Bodhanath Pal, sir. So today is the last session about the practical training in univariate and bivariate analysis with SPSS software. And our resource person already explained in details about all the module like introduction to statistics and SPSS data management systems and various tools, SPSS environment, like starting from data types, measurement of central tendency, data view, variable view, and important tools like data management, how to prepare your data, select and split file, how to do it and why you have to do it, select and split file, computation and transformation, code and decode. This is also important thing we have learned from Dr. Podnath sir. Then another thing, exploratory data analysis, and we have learned from Dr. Bodhanath sir how we can perform exploratory data analysis and the graphical representation of data like histogram, bar plot, line plot, pie chart, scatter plot, and various descriptive statistics and measurement of variability like shape, size of data, and how you can interpret this variability of shape like skewness, kurtosis, and about the distribution of your data normality test and why normality test is needed. We have learned from Dr. Pal. And also in financial statistics, we have learned how to perform hypothesis testing using bivariate analysis, like using chi-square test, phi, Kamersky, eta, kappa, relative disk, Kendall-Taw, a McNamara test, how we can perform it and how we can interpret it. Another important part, correlation and linear regression. Dr. Pal explained how we can perform linear tests like simple and multiple linearity tests and correlation and also regression analysis. And today we learned from Dr. Pal how we can perform the t-test, ANCOVA, MANOVA, MANCOVA. Already Dr. Pal explained about the ANOVA, and also we learn non-parametric tests like Mann Whitney U test, Wilcoxon sign rank test, and one sample run test, Kruskal test. So today's session 7, already 6 session over. If you want to still interested in this course, then you can join our recorded session, and Dr. Pal support you lifetime. You can, if you have any doubt, you can ask during the class and after the class and after few months also. If you face any difficulties, just click on this enroll button and join now. Thank you. Now I like to invite Dr. Pal to carry on this today's session. Sir, please start your session. So this is a great opportunity for us to directly learn from Dr. Bodhanath Pal sir. He has a long experience in this field. He has worked in Indian Statistical Institute, Kolkata. Sir, please start your today's session.
Good evening. So this is my data set. I open from SPSS packages, and there are so many variables, different type of variables, some continuous, some categorical.
Sir, excuse me, sir.
Yeah.
I think the recording is off.
Yes, sir. Please start your record.
Recording in progress. Okay.
Yes, thank you, sir.
Now we are going to analyze the T statistics. Okay. So first go to the analyze, and here compare mean, and there are so many different types of statistics t-test. First here, one sample t-test. So t-test is the parametric test statistic. That is, your target variable follow the normal distribution, and variance should be homogeneity, and check the outlier also. Okay. So t-test is related to the mean. So now we find the significant difference between the means. Okay. So this is my observed variables in the left side, and here is the test variable in this box. So from here we choose any continuous variable, that is systolic blood pressure. I putting here, and this blood pressure, there are 745 individuals. That's why you got mean and standard deviation also. Okay. So I want to compare this mean with the test value. Here is test value, means here that is your reference value. Okay, that is your reference value. Reference means, suppose you have any observed value like previous you got from the previous study, like this way. So you compare this one with this target value and your mean. Is there any significant difference or not? So first, your target value may be 120, because this is the systolic blood pressure. So I think this is the normal range, 120 by WHO. Okay. So I want to compare this mean and this value. Is there any significant difference or not? So here is some option in here. Not required. Then okay. So this is the output file. My target variable is systolic blood pressure, and there are 745 individuals. Mean is 114.12, and standard deviation 14.911, and standard error 5.4.546. So this is my target value. So I want to compare this and this, this and this. So this and this, is there any significant difference or not? So just test statistics t value here, minus 10.79, 759 t value, and degrees of freedom 744, and significant, that is to tell, that is 0. That is actually, this is not 0. Some value is there after 5 or 6 decimals. Since this is rounded, so showing this is 0. So it is obviously less than 0.05. or 0.01. Say that's why we can say this is significant. Okay, at 1% level. Significant means we reject the null hypothesis. We reject the null hypothesis and accept the alternative. So what is the null hypothesis? Null hypothesis means this value and these values are equal. This and this are equal, that is no difference. And alternative is this is not equal, this and these are not equal. So test statistics indicate that this is significant. That's why we reject the null hypothesis. We accept the alternative. That's why this value and this value are significantly different. This and these are significantly different. Okay. So when you have any reference value and you want to compare your observed mean, then you use one sample t-test. Okay. Then we can use one sample t-test. And 95% confident intervals of differences. That means this minus this, the difference is there. So 95% confidence means this is the lower limit, this is calculated value, this is also upper limit, this is also calculated value. Okay. So 95% chance your population mean fall in this range. Population mean fall in this range. This is the interpretation of one sample t-test. Now we go to the independent t-test. So this is another type. Compare mean between two groups. Suppose systolic blood pressure. I have two groups here. Two groups means male, female, maybe one group. Smokers, non-smoker also. Smoking status, that is another group. Smoking status here. Suppose I put here smoking status. Grouping variable, and my target variable is systolic blood pressure. This is systolic blood pressure. So when we perform the independent t-test, when we perform independent t-test, such type of if you have such type of data, suppose you want to compare by group. Compare by groups, then you apply the independent t-test. In such situation, we can apply independent t-test. In this data, systolic blood pressure must follow the normal distribution. And here, since there are two groups, that's why we check the homogeneity of variance between the groups. Check the homogeneity of variance. So here range is 1 and 2. One means smoker, and 2 means non-smoker. Then continue. Okay. Then continue. So check this one, result. Okay. So this is our output. So smoking status, that means yes and no. Yes 330 and no 415. And mean of the yes categories 11.06 and standard deviation 14.73, and mean of the no categories 116.56 and standard deviation 14.61. So now my objective is I want to find out the any significant difference between two means, or yes or not. Any significant difference between two means. Okay. So Then I go to the independent t-test. Here, first Leibniz test for the equality of variance. Since there are two groups, so two variances there. That is one standard deviation square means variance, and another is here. So our assumption is that two variants are equal. Two variants are equal. Okay. So check here, f value, and corresponding p value, that is not significant. So we can say we meet the homogeneity of variance. That is, both variants are equal since it is not significant. That means we meet our assumption. Okay, the homogeneity of variance. And another t-test here, minus 5 point something, and degrees of freedom 743, and probability also this is less than 0.01. Less than 0.01. Okay, so this is significant. So we can say the significant smoking status for yes or no, there is a significant difference. Okay, there is a significant difference, that is 1% level of significance. This is the interpretation. Okay, this is the interpretation. So if you want to sex wise, that is male and female, so check similar way, like this way, we can find the significant difference. In such situation, we can apply the independent t-test. So when we apply the independent t-test, we need two types of variables. First target variable is continuous variable, like systolic blood pressure, height, weight, anything. Okay, and another variable should be categorical variable. There are two categories only two categories. Okay, like gender, male, female, say, and smoking status, yes or no, similar things. Okay, so in such situation, we can apply the independent t-test. And another is here, pair t-test. So when we apply pair t-test, pair t-test, actually this is the different points of same observation. We take the different point, different times of measurement. Okay, so suppose here is 745 individuals. We take the measurement first time, blood pressure measurement, and after 1 month, again we check the blood pressure for same individuals. And before and after, we got the two means and standard deviations also. Then we want to check the any significant difference between two means or not. Okay, between two means or not. So suppose here here we have data systolic blood pressure, here is SBP1, we have taken the first time measurement, and SBP2 taken the second time measurement. Okay, so now from this mean and from this mean, is there any significant difference or not? I want to check. Okay, so in such situation, we can apply pair t-test. In such situation, we can apply pair t-test. So now we can apply PRT test, analyze mean and PRT test. So I put here first SBP1 and second SBP2. So then okay. So check here. PRT test, pair sample statistics, pair SBP1 mean is this one 114.12. Number of observations 745. Standard deviation is here 14 point something. And SBP2 also mean is 11.5 and same samples and standard deviation 13.99. Okay. So correlation between these variables is this one correlation. This is also significant. Now here we check the difference, mean difference, that is minus 1.58. That is this minus this equal to this one, and standard deviation this one, and t value is here minus 2 point something. So here is degree of freedom 744 and significant level is 0.023. That is, this is also significant because this is less than 0.05. So we can say this is the significant difference at the level of 2.3%. Okay. So both measurements, both mean of the both measurements are significantly differ with 1% level to 5% level of significance. This is the PRT test. Okay. So we apply one sample t test, independent t test, and this is called PRT test. Now I go to the independent t test. Here, analyze independent sample t test. Here, suppose here is only smoking status group 2. Yes or no, binary response. And if you have more than one group or two groups, suppose body mass index, there are 3 groups. Okay, so 1, 2, 3. So how to compute this one? Independent test. First we compute 1 versus 2, then 1 versus 3, and 2 versus 3. So many computation required for many t-tests, but find out the significant difference. So avoiding for such situation, we can apply the one-way ANOVA. We can apply one-way ANOVA. So this is also parametric test, one-way ANOVA. The assumption is same. Assumption same. Now I go to the one-way ANOVA. Again here, just compare mean. It is one-way ANOVA. So again, I put here my target variable, systolic blood pressure, and BMI. If we consider the BMI category, there are 3 categories. There are 3 categories. Okay. So we got the 3 means also here for 3 categories, each category. Okay. So contrast here, not required. Post hoc is there. So I put here step test. Okay. And option homogeneity of variance and descriptive statistics. Okay. Then continue. And okay. So there are 3 groups. BMI, group 1, BMI less than 18.5, group 2 18.5 to 24.9, and greater than 25, greater than equal to 25. There are 3 groups, and the mean difference is here. For first group, mean this to this difference is here, mean difference, and this to this mean difference is here. Similar this way. Okay. Oh, this is the main table, 1A ANOVA. There are 3 groups, 1, 2, and 3. First group, there are 330 individuals. In the second group, 393, and the last group, only 22 observations is there. And the corresponding mean is here, corresponding standard deviation here. Okay, and standard error also, minimum, maximum, like this was. And here is test of homogeneity test, that is Leibniz test. This is also not significant, marginally significant or not significant. So meet the assumption also. Okay, meet the assumption also. And this is the ANOVA table. This is the ANOVA table. Between groups means there are 3 groups. So degrees of freedom 3 minus 1, and within groups, that is total, that is 745 minus 3. Okay. So mean square error, that means this divided by this equal to this one, and this divided by this equal to this one, and mean square error, mean square, this divided by this equal to this divided by this equal to F value. This is the ratio between 2, and the corresponding probability here. This is also significant. That means we got the ANOVA table, F value, and corresponding significant probability value. This is also significant. That is less than 0.05. So from here we can say at least one pair has the significant difference. If we perform the independent t-test, that means at least one pair has the significant difference. That is F value indicating this one. If it is not significant, that there is no significant difference between any pair. Okay, any pair. So check, is it significant? So go to the which pair is significant. We go to the post hoc test further, and this is the post hoc test, multiple comparison, and multiple comparison. First group, this is the first group versus second group. The mean difference is this one, and the corresponding t value here is not showing the t value, but showing the probability value only. This is significant. This is significant. So first versus second group is significant. First versus third group also significant. Okay. Here also second versus first. First versus second means second versus first, same is here. And second versus third also here. And third versus first and second. All these are significant. So we can say the group difference exists. What is the hypothesis? Our hypothesis that all means are equal. That means there are 3 means here. All means are equal, and null hypothesis, all means are not equal. So this is significant. We reject the null hypothesis, accept the alternative. That means all means are not equal. So we can say the all group means are significantly differ. All group means are significantly differ at 1% level or 5% level, 1% level. This is the one-way ANOVA. Apart from that, two-way ANOVA also. So when we apply two-way ANOVA, if your independent variable is more than one, 2 independent variables, not one. If you have 2 independent variables, that means 2 categorical variables, then we can apply two-way ANOVA. So how to perform the two-way ANOVA? Check here. Analyze and general linear model, univariate analysis. So put here dependent variable. Put here dependent variable, systolic blood pressure, same thing here. And here is so many boxes. Here, if you have categorical variable, we put the fixed factor, and others are not required for the two-way ANOVA. These are not required for the two-way ANOVA. So we put here and fixed factor if we have categorical variable. So I put here categorical variable BMI also, BMI, and here is another categorical variable, age category. There are 4 categories. So in BMI there are 3 categories, and age there are 4 categories. So now how many hypotheses is here? So there are 3 null hypotheses, okay, for two-way ANOVA, and 3 alternative. So first null hypothesis is the mean effect in BMI, and age category also main effect, and third, there is any interaction effect. There are any interaction effect. Okay. So now model, go to the model and customs. So put here main effect here, main effect for BMI, and main effect for age, and another interaction here, interaction both age and BMI. Okay. So then continue. Contrast, not required. Plots not required. Post hoc, if you wish, this and this. Save again. Save not required. Okay. Then okay. So check here. Here is the two ANOVA. First BMI category. There are 1, 2, 3 categories, and value labels is here. 1 means less than 18.5 BMI, and 2 means this, and 3 means this, and number of observations is here, and age category 1, 2, 3, 4, age 19 to 30, that is first category, and greater than 60, fourth category, and there are 31 observations only. Okay, so this is the main ANOVA table. ANOVA table. So check here. There are similarly here, F value is here and significant is here. So first I check the main effect of BMI. So BMI is the significant. Okay, and age category also has the significant effect, but in their interaction has no interaction effect, and there is no significant. So from this analysis, we can say the BMI has the significant effect of systolic blood pressure. Age category has also the significant effect of systolic blood pressure, but their interaction they have no effect. Interaction has no effect on systolic blood pressure. Is it clear? Now I find to check. There are 3 categories. There are 4 categories. So from BMI post hoc test, all categories are equal importance. 1, 2, 3, because all the cross significance here. So all categories are equal importance. That means all BMI value are important for the systolic, measure the systolic blood pressure. So BMI is the very important factor for controlling the systolic blood pressure. Okay. From this result, we got from this result. And check here, homogeneous subset. So check here, there are 3 categories. So first and second category got the one, create the one cluster, and last category created another cluster. That is these and these are homogeneous group, and this is maybe heterogeneous from this one. And check the significant difference. So check age group 1 versus age group 2, that is not significant. Age group 1 versus age group 2, that is significant. Age group 1 versus age group 4, that is also significant. And 2 versus 1 and 1 versus 2, same here, 799. Here is also 799. 2 versus 3, this is significant. And 2 versus 4, this is also significant. And 3 versus 2 also significant. 3 versus 2 also significant. And 3 versus 4 not significant. And again, last category, same things. We have 2 significant. Okay. So check here, the first age group significant with other 2 groups. Okay. And this is also significant with 2 groups. And this is significant with 2 groups. And this is also significant with 2 groups. So all these ages are equally important for the systolic blood pressure. Okay. So all groups are equally important because here is 2, here is 2, here is 2. Suppose if it is 3, all 3, we can say the age category 4 is most effective than others on influence of the dependent variables. Okay. This is the interpretation of the 2A ANOVA. And here is also homogeneous group. The first and second create one subset, and last 2 create another subset. This is the 1A and 2A ANOVA. Now we can say multi-way also. If you have more than 2 independent variables, then we can say multi-way. And you put only here, you can perform from these spaces also. Now we go to the ANCOVA. Now we go to the ANCOVA. So when we apply ANCOVA, suppose in 1A ANOVA, here in the 1A ANOVA, 1A ANOVA, here this is perform 1A ANOVA. If value is significant. If it is not significant, the 1A ANOVA is not required, not necessary. Okay. If F is not significant, 1A ANOVA not necessary. It is significant, that we can perform the if it is significant or if it is not significant, ANCOVA is not necessary. Okay. If it is significant, you can apply ANCOVA. This is 1A ANCOVA. So when we apply 1A ANCOVA, suppose my systolic blood pressure, this is my dependent variable is systolic blood pressure, SBP. This is related with so many other continuous variables. Okay. If we found any confounding variable, that is any highly correlated value with other variables, then we can say this is the confounding variable. Now we want to eliminate the effect of the confounding variable. Then I want to find out the perfect F value. Perfect F value. Okay. So suppose again we go to the one-way ANOVA. From here we can perform this one. So I remove this one and SGP, and suppose here weight circumference. Suppose weight circumference is highly correlated with this one, systolic blood pressure. That means highly correlated with some effect is there. So now we eliminating the effect of the weight circumference on systolic blood pressure, or we are controlling the variable weight circumference, then we find out the one-way ANOVA, or after controlling the effect, we find out the one-way ANOVA. So check this one. Okay. The following factors or covariates are not used in the model. Why not? Oh, okay. Got the value. So check here. WC, that means waist circumference. This is not significant. That is, waist circumference has no significant effect on the systolic blood pressure, and BMI also significant. Okay. So after eliminating the slight effect, that is F value is 29.03. Okay. So our previous value 29.33. Okay. Since it is no effect, that's why the value may be constant. Okay. So when we apply ANCOVA, if we controlling the variable and find out the effect of the dependent variable using the independent variable, then we can apply the ANCOVA. That should be one way or two way, same things. Okay. So covariates may be 1, or confounding variable may be 1 or greater than 1. That is no problem. So this is the ANCOVA. Okay. So we already discussed about one sample t-test, independent t-test, pair t-test, one-way ANOVA, two-way ANOVA, and one-way ANCOVA also. Is it clear? Now we go to the MANOVA. When we apply MANOVA, just reverse this one. When you have, here is in ANOVA, we have one dependent variable, a continuous. Suppose you have more than one dependent variable, then in such situation we can apply MANOVA. In such situation, we apply MANOVA. So I again go to the analyze and linear model, that is not univariate. I go to the multivariate. So let's check here. The dependent box is large, so we can put so many dependent variables in this here. Here. So check here. Again, I put here systolic blood pressure and diastolic blood pressure and pulse rate also. Pulse rate. Pulse rate also. That is all the physiological variable. And fixed factor, that is independent variable, that is one categorical variable, more than 2 categories. Again, I put here BMI category, body mass index. Body mass index. Okay. Now, model, not required. Contrast, post hoc. If you require, you can put the post hoc also, otherwise, okay. So check here. There are independent variables, 3 categories, and the number of observations. And multivariate test, BMI for BMI category, field light race, Wilks lambda, Cotillion test, and all are nearly similar. I check the significant here. All these are significant. So we check lambdas. This significant indicate, that means any pair have the significant difference. Okay, any pair have the significant difference. This Wilks lambda indicating this one. So check here. This is the dependent variable. There are 3 dependent variables: systolic blood pressure 1, diastolic blood pressure, and pulse rate. So I check here BMI. Here BMI. So check here BMI and systolic blood pressure. The value is this is the significant. And BMI with diastolic blood pressure, this is also significant. And BMI with pulse rate, this is not significant. So we can say the BMI has the significant effect of blood pressure, both systolic and diastolic, and no effect on the pulse rate. Okay, BMI has no effect on the pulse rate. This is the main things of the MANOVA. MANOVA. Okay, this is one way. Again, it's similar to ANOVA. You can put 2 independent variables, then got the results, main effect, and interaction also. Is it clear? And similar again, if we put any multivariate here, if we put any covariates here, covariates means confounding variable. That means we controlling the effect of this. Then we can put here controlling variable. This is the MANCOVA. Okay, this is MANCOVA. If these are the significant, we can go to the MANCOVA. If these are not significant, that is not necessary. This is not necessary. Okay. So this is the ANOVA and MANCOVA. Is it clear? Now, so I compute these are the all parametric test statistics. If we fail, suppose your data does not follow the normal distribution or fail the assumption, then we go to the non-parametric test statistics. Non-parametric means that is distribution free. Okay, that is distribution free. Your result will be same, but method should be different. Result will be same, but method should be different. So we go to the non-parametric test also. Here, analyze, analyze, non-parametric. Legacy, first independent t-test. Just alternative independent t-test. This is the Mann Whitney test. This is the Mann Whitney test. So again, I put systolic blood pressure, and here grouping variables: smoking status, here is smoking status, just alternative of independent t-test, and group is 1 and 2. 1, 2, then continue. And Mann Whitney test already highlighted. Okay. So go, okay. Check the result. Check here. The yes, the 330 number of observations, and no, 415 number of observations. The mean dank, and this is the mean dank also. Mean dank means our according to this, our systolic blood pressure will be ranked. Okay. So ranked of the this group, and ranked of the mean dank of the this group. So check this, is there a significant difference or not. So Mann Whitney tests tell you using the Z value, this is also significant. Okay, this is also significant. So we can say the smoking status has the effect on systolic blood pressure. That is, there is a significant effect on systolic blood pressure. So result is same. That is, here is significant also. And if we go to the independent t-test, that is the significant also maybe. This is the value. Okay, this is the independent t-test value. This is also significant, and here is also significant. This is also significant. That is the Mann Whitney test. Is clear? Now I go to the pair t-test. Pair t-test is similar to here. Related samples. That is related samples here. So Wilcoxon test, that is already default here. Wilcoxon test. Okay. So again, I put here systolic blood pressure 1 and 2. Then okay. Check here. SBP versus this are negative, and this is the Z value. This is also significant. Okay. This is also significant. So the measurement of the mean of two measurements of systolic blood pressure has the significant difference. Same results is there also, but method is different. Now I go to the ANOVA alternative. Here is non-parametric, and you can see there is K independent sample. Again, I put systolic blood pressure. And BMI also. BMI category also. Then define range 1 and 3. Then continue. That is the Kruskal-Wallis test. Instead of ANOVA, we use Kruskal-Wallis test. Okay. Then okay. So there are 3 categories, and this is the test chi-square, and this is also significant. So we can say the BMI has the significant effect on systolic blood pressure. BMI has the significant effect of systolic blood pressure. So this is the alternative of, and another is repeated measure. Repeated measure, we have no data, such type of data. And another part, ANCOVA is not possible here. ANCOVA is not here. Or MANCOVA or MANOVA is not here. Okay, in the non-parametric test. So we finish this. One sample t-test, independent t-test, pair t-test, 1A ANOVA, 2A ANOVA, 1A ANCOVA, 2A ANCOVA, 1A MANOVA, 2A MANOVA, and non-parametric test, Kruskal-Wallis test, and Mann Whitney test, Wilcoxon test, like this way. So, any questions regarding this one?
Dear participant, if you have any queries, any question, you can ask to our resource person.
Sir, non-parametric test is used only when the data is not normally distributed, no?
Violation the assumption. Yeah. Normally, it is one of them.
Okay, sir.
Any other question? So I guess no question is there. So, sir, so we should stop there.
Okay, can I stop?
Yeah, sir. No question is there. So, dear participants, we already completed our 7 days online practical training using SPSS software. So, you can watch the recorded session. Our registration still is open. You can join also. And our resource person, Dr. Bodhanath Palsar, always open to help you for your research. Thank you for joining with us.
Okay. Thank you.
Thank you, sir. Thank you.